So today our first speaker is Parvathi S. So she is currently a third year BSc Mathematics student at St. Teresa's College, Ernakulam, affiliated to NG University, Kerala. So she has attended level O in the MTTS 2023 at IIT Dhanbad. So her topic is some applications of intermediate value theorem. Over to you, Parvati.
Hi everyone. Today I am going to take my session on some applications of intermediate value theorem. Intermediate value theorem is a theorem which is used in almost all domains, not only in mathematics but all domains of science to prove some results. So today I am going to prove two of the important results of intermediate value theorem. So first let us look at what does intermediate value theorem states. So the statement is that let AB be a closed and bounded interval and a function is defined from closed interval AB to R such that the function is continuous. If f of A not equal to f of B, then f attains every value between f of A and f of B at least once in the open interval AB. So let me explain it in a simpler terms. So we have a function from closed interval AB to R. Then if we have the value of the end function at the endpoints are g of A and g of B, and if the function is continuous, then any value between g of A and g of B will have a pre-image in the closed interval AB. Let g be a continuous function from closed interval AB to R. Let lambda be a real number between g of A and g of B. Then there exists a C belongs to AB such that g of C equal to lambda. Now I am going to state an important corollary. It's not actually corollaries. In some textbook, this is mentioned as the statement of intermediate value theorem. It states that let f be a function from closed interval AB to R be continuous such that f of A is less than 0, which is less than f of B. Then there exists a C belongs to AB such that f of C equal to 0. I will be using this corollary to prove two of the applications. So today I will be explaining the applications, existence of nth root for non-negative real numbers, and the second one will be any polynomial of odd degree with real coefficients has a real 0. Okay, let's look at the first one. Existence of nth root for non-negative real numbers. If I have alpha greater than or equal to 0 and n be a natural number, then there exists beta greater than or equal to 0 such that beta to the power n is equal to alpha. This is my statement. So we will be proving this proof. So I will be proving this by considering a continuous function f from closed interval 0 to infinity to 0 to infinity defined by f of x equal to x to the power n minus alpha. From the corollary that we have seen earlier, we need a closed interval AB such that f of A will be negative and f of B will be positive. So now I am going to take such an interval. So in order to find that, I will be taking A equal to 0. If my A is equal to 0, then f of 0 will be equal to minus lambda, which is less than or equal to 0. Now I have to find the upper bound B. According to the Archimedean property, there always exists a natural number n such that n will be greater than alpha. If my n is greater than alpha, then I can say that n to the power n will be greater than or equal to n greater than alpha. So now I am taking my upper bound b to be n, then n to the power n minus alpha will be greater than 0. That is, f of n is greater than 0. So now I got that f of 0 is less than or equal to 0, which is less than f of n, and alpha is belongs to 0n. Now by using the intermediate value property, I can say that there exists a C belongs to 0n such that f of C equal to 0. That is, f of c equal to c to the power n minus alpha, which is equal to 0, which implies that c to the power n is equal to alpha. Now what do we have got? We have got that alpha can be written as the nth power of a real non-negative real number. This is what we have to prove. Hence we have proved the existence of nth root for non-negative real numbers. Now my second result is that any polynomial of odd degree with real coefficients has a real 0. Now let us look at the proof of this. So first I am considering the general form of polynomials. P of x equal to x to the power n plus a n minus 1 x to the power n minus 1 plus etc. plus a naught, where all the aj's are real numbers and j varies from 0 to n minus 1. Now I am taking x to the power n common. Then my p of x will be equal to x to the power n into 1 plus a n minus 1 by x plus etc. plus a naught by x to the power n. Now I am going to estimate the value of this function. So I have, by using the law of triangular inequality, I can say that mod of n minus 1 by x plus etc. plus a naught by x to the power n will be less than or equal to the mod of the individual terms. That is, will be less than or equal to mod n minus 1 by mod x plus etc. till mod a naught by mod x to the power n. Now, I am assuming my mod x to be greater than or equal to 1. Why am I doing that? Because if my x is less than 1, then my x to the power n will be less than x to the power n minus 1. So in order to avoid that, I am assuming mod x to be greater than or equal to 1. If my mod x is greater than or equal to 1, then my mod x to the power k will be greater than mod x. Then 1 by mod x to the power k will be less than or equal to 1 by mod x. So I am replacing all the denominators by mod x. I will get mod a n minus 1 by x plus etc. plus a naught by mod x, a naught by x to the power n will be less than or equal to mod a n minus 1 by mod x plus etc. plus mod a naught by mod x, which will be less than or equal to, since my denominators are same, I am adding up the numerators, which will be less than or equal to mod a n minus 1 plus etc. plus a naught by mod x. I am naming my numerator as c for convenience. So my old term will be less than or equal to c by mod x. Now, I am taking an n belongs to natural numbers such that c by n is less than 1 by 2 for all x such that mod x is greater than or equal to n. Why am I taking 1 by 2? Because if you look at this modulus, we can see that as the denominator tends, that means x tends to infinity, since there are only finite terms, the value of the function will be less than 1 by 2 after a point. So I am taking this number 1 by 2. So my c by n, since my c by n is less than 1 by 2, my c by mod x will also be less than 1 by 2 for all mod x greater than n. So after expanding the inequality, I will get minus 1 by 2 less than n minus 1 by x plus etc. plus a naught by x to the power n less than 1 by 2. Adding 1 throughout, I will get 1 by 2 less than 1 plus n minus 1 by x plus etc. plus a naught by x to the power n less than 3 by 2. So now I am naming my 1 plus a n minus 1 by x plus etc. plus a naught by x to the power n as g of x. Then I can write as 1 by 2 will be less than g of x less than 3 by 2 for all mod x greater than or equal to n. And I am naming this condition as equation number 1. So I have two cases in this to be applied on equation number 1. That will be when x greater than or equal to n If my x is greater than or equal to n, where n is a natural number, I can say that x will always be greater than 0. If x is greater than 0, then x to the power n is also greater than 0. If I multiply my equation 1 with x to the power n, then I get 1 by 2 x to the power n is greater than x to the power n g of x less than 3 by 2 x to the power n. Okay, then I have x to the power n g of x is my p of x. So my p of x will be greater than 0 since 1 by 2 x to the power n is also greater than 0. Now I have my second case when x is less than 1 by 2. Sorry, my x is less than minus n. For my x less than minus n, in the corollary of intermediate value theorem, we want the f of a to be less than 0. So for my x to the power n to be less than 0, where n is minus n, I need my n to be odd. This is the only place that we are applying our n must be odd. So since n is odd, x to the power n is negative. Multiplying our equation 1, that is 1 by 2 less than g of x less than 3 by 2 with x to the power n, I get 3 by 2 x to the power n is less than x to the power n g of x less than 1 by 2 x to the power n. From here, x to the power n g of x less than 1 by 2 x to the power n less than 0, which implies my p of x is less than 0. Now, we have got that at my minus n, the value of p of x is less than 0, and at my value of n, my value of p of x is greater than 0. By applying the intermediate value property, there exists a c belongs to open interval minus n such that p of c will be equal to 0. We have got that p of c is equal to 0. Then we can say that c is a real root of p of x. Now this is how we prove that any real polynomial of odd degree will have a real root. So this is proved. Now I have mentioned that intermediate value property has other applications beyond mathematics. Just to say that I have written some of them. It's used in fluid dynamics, thermodynamics in physics. It is used in modeling population growth in biology. It is used in control systems in engineering. These are some other applications, just I have mentioned it. To conclude, the intermediate value theorem is a versatile mathematical concept that finds applications in many fields whenever you need to prove the existence of certain values, states, or phenomena without necessarily determining the exact values themselves. So that's all. These are the references that I have used. Thank you.
Yeah, thank you, Parvati. That was nice. Anybody has any doubts? Okay, then I think we can move
Yeah,
on.
yeah. One thing, Pia.
Yeah.
Maybe Parvati, you can share your presentation. Can you go to your first application? First application. Yeah. Next page. Uh, yeah. So, how did you conclude that if 0 is less equals to 0?
Here I am taking my lower bound to be a, which is equal to 0. Then I have f0, since my function is f of x equal to x to the power n minus alpha. If I take the value of x as 0, then my value will be minus alpha. F of 0 will be minus alpha, which is negative. I have taken alpha to be greater than or equal to 0. So if it is minus alpha, then it will be less than or equal to 0. So f of 0 will be less than 0.
Correct. Okay.
Parvati, one more thing. Can you go to previous slide? Um,
Here,
yeah. So here you define from some domain to codomain, right? Is that correct?
yeah, I think so.
What if x is equal to 0? Then you just told something, right? F of x will be.
Minus alpha.
So is that in the codomain? Codomain is from 0 to infinity, right?
Yeah, it must be open interval.
Open interval or something else?
It must be from R to R.
R2R makes sense.
No.
Okay.
See, Parvati, when you are allowing your alpha to be greater equals to 0, and you want to find value at x equals to 0, then fx is taking the value is minus alpha, right?
Yes.
So minus alpha, then alpha is greater equals to 0, then what can minus alpha be?
Negative.
Any negative number it can be. Then the way you have defined, you have to allow your codomain to be R.
Oh, okay. Okay, sir.
Yeah. So in general, you can define from R to R also, but you have defined from a particular set. So
Yeah, sorry, sir.
yeah, maybe for your proof, it is enough to consider this.
Okay.
But can you go to your statement? Statement of intermediate value property.